Hi guys, this video is going to be practice question for heat transfer conduction. Our first question is temperature distribution of a slab is given as this relation is given as temperature distribution T is equal to 4 minus 10x plus 2x square plus 10x cube. Thermal diffusivity alpha is given as 2 into 10 to the power minus 3. Temperature gradient of slab at x is equal to 1 meter. We have to find out in degrees Celsius per hour. So our one dimension equation is del square T by del x square is equal to 1 by alpha del T by del T. Del T temperature and del small t is our time. This is temperature gradient. So the temperature profile is given. So using this equation we are going to differentiate it, double differentiate it, and then we are going to get our del square T by del x square, which is equal to 100 at x is equal to 1. Then putting this 100 in our equation, we are going to find our alpha. Alpha is given to us. We are going to find our del T by del T temperature gradient, which comes out to be 0.2. Next is a brick wall. Its K is given as 0.9, thickness is 0.27 meters. Separate warm air in room from cold ambient air on winter day. Outside temperature is minus 2 degrees Celsius and room need to be maintained at 25 degrees Celsius. Heat transfer coefficient is given as 20 watt per meter square Kelvin, and heat loss we have to calculate. So this is the room. Outside it convection is taking place and inside conduction is taking place. Outside temperature is minus 2 degrees Celsius and inside temperature is 25 degrees Celsius, and the thickness is 0.27 meter. So this is conduction plus convection based question. So the overall heat transfer coefficient, which is U, it is calculated as 1 by U is equal to 1 by H heat transfer coefficient into L by length by K. So 1 by U, we have to put the values of H, which is given to us, length, and K, after which we calculate our U. And to calculate our heat loss Q, which is equal to UA delta T, then putting all the values of U, area, and change in temperature 25 minus of 2, we get our Q, that is heat loss. Next question is steady state 1 dimension heat conduction across 1 and 3. These are two slabs given to us. So steady state heat conduction is taking place between 1 and 3. Composite slab consisting two slabs A and B in perfect contact. We have to calculate T2. So let's zoom into this diagram. So two slabs are given, and on this surface temperature T1 is given as 130 degrees Celsius, and on third surface temperature T3 is given as T3 is given as 30 degrees Celsius, and K for slab A is given as 20 watt per meter Kelvin, and K for slab B is given as 100 watt per meter Kelvin. The thickness of slab A is 0.1 mm and slab B is 0.3 mm. So we are going to make this circuit diagram for our resistance diagram. So this surface, we have taken resistance for this surface is taken as RA, and for slab B is RB. So our circuit diagram would be T1, T2, T3. Resistance between T1 and T2 RA, between T2 and T3 RB. Resistance we know that is equal to L by K. So the slabs are in perfect contact. So using the formula T1 minus T2 upon RA, temperature difference between these two divided by resistance is equal to temperature difference between these two divided by resistance between them. So putting on the values of T1 and Ra, which is equal to L by K. Length of slab A is 0.1 and K is given as 20. And for this is okay. And for slab B, temperature T3 is given, thickness is given, and K is given. So putting all the values, we calculate our T2. Next question is, this is our slab and it is heated by a fluid flowing outside, and the fluid flowing outside has temperature of 45 degrees Celsius and heat transfer coefficient H is given as 10 watt per meter square Kelvin. Thickness of slab is 0.2 meter and temperature at this surface is Tf, which we have to find. K is given as 2.5 and temperature for this surface we have 25 degrees Celsius. So this is outside the solid surface, heated fluid is there, and so between this surface convection would take place and inside the slab conduction would take place. So making a network diagram for this, for convection from this outside fluid to the surface from T infinity to Tf, the resistance is 1 by Ha, convective resistance. Then from Tf to Tq, between the slab conduction is taking place, so conductive resistance is L by Ka. Now temperature difference by resistance between them for this portion would be equal to temperature difference between this part upon resistance between them would be equal. So T infinity minus Tf upon resistance between them would be equal to Tf minus Tq upon resistance between them. So putting in the values, we can calculate our Tf. Next question is, two rectangular blocks of same dimension and same temperature difference is given and their configuration is different. They are of same dimension but their configuration is different. Configuration 1, we have two blocks and first block conductivity is K, second one is 2K. They are in, and then second configuration, they are kept one upon another. 2K is above, then we have K configuration. These are two slabs of same dimension kept in two different configuration. So in configuration 1, for hot end to cold end heat transfer, time is given as 9 seconds. So we have to find heat transfer time for configuration 2. This is our question. So configuration 1 is basically in series. So to calculate overall resistance, we would add the resistance of slab 1 and slab 2. So resistance is L by Ka, conductive resistance L by Ka, and plus for slab 2 resistance is L by 2Ka. So taking their sum, our R1 for configuration 1 resistance come out to be 3L by 2K, and for configuration 2, which is in parallel, so to calculate this overall resistance, 1 by R2 would be equal to 1 by resistance of first block plus resistance of second block. This is for parallel configuration 2, our resistance come out to be L by 3Ka. Now we know that Q by T, heat transfer with respect heat transfer upon time, is equal to delta T by Rth. So this would give us T1 by T2 for configuration 1 T1, and for configuration 2 T2 would be equal to R1 by R2. From this relation we have found that time is directly proportional to resistance. So from there we can calculate our time 2 for our configuration 2, which comes out to be 2 seconds. Next question we have is, a square plate of 1000 watt electric heater and 10 by 10 square plate of 1000 watt electric heater of 10 centimeter by 10 centimeter dimension is inserted between two slabs. Slab A of 1 thickness, its K is given as 25. Slab B of 2 centimeter thickness, K is 0.2, and outside heat transfer coefficient on side A and B are 250 watt per meter square Kelvin. Surrounding temperature 30. We have to find maximum temperature. So let's understand this question by the help of a diagram. So we have two slabs A and B, and between them a 10 centimeter into 10 centimeter dimension, 10 by 10 dimension electric heater is inserted, and it is of 10,000 watt electric heater is inserted, and its dimension is 10 by 10, and thickness of our slab A is 1 centimeter, its K is given as 25, and thickness of our slab B is given as 2 centimeter, and its K2 is here 0.2 watt per meter Kelvin, and the surrounding temperature outside this slab is 30 degrees Celsius, and H1, that is heat transfer coefficient at side of A, is given as 200 watt per meter Kelvin, and at side 2 is given as 50 watt per meter Kelvin. So we know that Q is equal to delta T by R. Okay, now we are going to draw our resistance network for this diagram with help of this diagram. So first, like, if we see this surface, this is outside. From outside of the solid surface, convection would take place in this portion, after which from this surface to this surface conduction would take place. Then again in between these surface again conduction would take place, and then in between this surface again conduction would take place. So, sorry, let me repeat. Between this surface convection would take place, and between these surfaces convection would take place. Between both these surfaces convection would take place, and between these surfaces our conduction would take place. So we are going to draw resistance network diagram. From T infinity to temperature of slab A, convection is taking place. Then from TA to our maximum temperature, which is of electric heater, conduction is taking place. Then again from this surface to our slab B, conduction is again taking place. Then from slab B to outside, convection is taking place. So in this diagram, from T infinity to TA, convection and resistance is given as 1 by H1A. Then from TA to T max, temperature of slab 1, to maximum, which is of electric heater, conduction is taking place, L by K1, K1A, which is our resistance. Then from the electric heater to the second B surface, again conduction is taking place, resistance given as L by K2A. And then for slab B to the outside surrounding, convection is taking place from TB to T infinity. So convection given as 1 by H2A. So these are taken as two entities, and to calculate Q, we are going to take sum of this part and this part. So Q is R, basically delta T by R. So delta T would be T max minus T infinity for this part, T max minus T infinity by sum of resistance between them. Then plus for this portion, the delta T would be T max minus T infinity upon sum of these resistances. So Q would be T max minus T infinity upon 1 plus H1A plus L by K1A plus T max minus T infinity upon L by K2A plus 1 by H2A. Now substituting all the values, Q we know is given to us 1000 watt for the electric heater. Now substituting all the values, We know our T infinity surrounding temperature 30 degree. H1 is given to us 200, and area is for slab 1 is 10. Then K1 is given to us, and similarly for the next slab we have our K2 and area is 20. Then putting all the values, we can calculate our T max. So next question is heat generated uniformly in long cylindrical rod. Its diameter is given as 10 mm. At rate of Q0 is given as 4 into 10 to the power 7 watt per meter cube. K is given as 25 watt per meter Kelvin, and it is a steady state. Temperature difference between the center and surface of rod we have to calculate. So this is our rod, and T0 is temperature at center, Ts is temperature at surface. So we have to find the difference between these two surfaces, temperature difference between the surface and the center. R0 is radius, so diameter is given to us, which is 10 mm, so R0 would be 5 mm. Now for cylinder with heat generation, we know this formula. The temperature at center T0 is equal to Q0, that is heat flow rate, into radius square upon 4K plus temperature at the surface. So we have to find T0 minus Ts, which will be equal to Q0. Q0 is 4 into 10 to the power 7 into radius square. We have converted millimeter into meter upon 4 into K is given to us. Then T0 minus Ts would be 10. Okay. Then next question is hollow sphere made up of two material. For the first material, K is given as 70 watt per meter Kelvin. Internal diameter is 10 centimeter, outer diameter is 30 centimeter. So we have two hollow spheres, like a hollow sphere made up of two material. So the outside material, the diameter is given to us as for this, like these are two material. So for the outside material, our radius is given as at outer diameter is 30. Wait, sorry. So guys, there are two material used for to making a hollow sphere. So the inner layer is called first surface R, and the outer material is second surface. So the first surface radius R1 is given as 5, and its outside radius is given as R2 is 15. So basically this is a hollow sphere, and its R1 is 5, R2 is 15, and temperature inside is given as 300 degrees Celsius, and K of this part is given is 70. Then outside of it another layer is laid out, and the outer layer, the finalmost outer layer, has radius of 20 centimeter, and its K is given as 15, and the temperature outside this whole hollow sphere is 30 degrees Celsius. Okay, so Q we know is delta T by R total. R total would be resistance of this first layer plus resistance of second layer, R1 plus R2. So to calculate R1 for the first layer, we are R1 would be R2 minus R1 by 4K R1 R2. R2 is 15, R1 is 5, R2 minus R1 by 4K R1 R2. We would get our R1. Then for R2 it would be R3 minus R2 for this surface upon 4 pi K R2 R3. Putting in the values, we would get our R2. From here we can calculate our R total, which is R1 plus R2. And temperature difference, we know the In inside temperature is 300 degrees Celsius and outside temperature is 30 degrees Celsius. So delta T would be 300 minus 30 upon R total we have calculated. So putting in the values, Q comes out to be 11.25. We have a few questions based on insulation, lumped capacity and fins. Let's just quickly go through those questions. 10 mm diameter electrical conductor is covered by insulation of 2 mm thickness. Conductivity of insulating surface is 0.08 watt per meter Kelvin. Convection coefficient at insulation surface is 10 watt per meter square Kelvin. Addition of further insulation will we have to find if it would addition of further insulation would increase or decrease the heat loss. So we have our 5 mm thickness, 5 mm radius surface rod, and outside it a 2 mm thickness insulator is covering it, and so the total radius would be 7 mm. So we know that critical radius of insulation RC is K by H, and so RC comes out to be K is given to us, conductivity is 0.08 by H, heat transfer coefficient is 10, so RC comes out to be 8 mm. What it means that for Q versus R, and our overall radius is 7 mm, so till 8 mm our Q at RC, which is at 8 mm, we get our Q max, maximum heat transfer, which is Q max is at RC. So it means that if we would further add insulation till the radius of 8 mm, like if we would increase the insulation for 1 more mm, till then heat transfer would increase. But after that, if we further increase the insulation, then heat transfer would decrease. Next question is, a steel ball 10 mm diameter at 100 K is required to be cooled to 35 Kelvin by immersing it in water at 30 Kelvin. H heat coefficient is given as 100 watt per meter square Kelvin. Conductivity K is given as 4 watt per meter Kelvin. Time constant tau is 2 seconds, and time required to reach final temperature we have to find out. So for lumped capacity, we know this formula, Ti minus T infinity upon T minus T infinity is equal to exponential of HA rho V Cp into T, and Ti is our initial temperature, T infinity surrounding temperature, and time constant, for time constant we have this formula, rho V Cp by HA. So this whole term is basically our 1 by tau. So we know the value of tau, and we know our inside temperature, initial temperature 100, and surrounding temperature 30, and temperature which we have to calculate at is T is given as 35, and tau we know is 2. So putting in the values, we can calculate our time to reach the final temperature, which comes out to be 5.27 seconds. Next question is, heat loss for fin Q is 3 watt, fin effectiveness is given as 2, and efficiency is given as 0.25. Heat loss, we have to find heat loss from the fin keeping the entire fin surface at base temperature. So we know that if entire surface is at base temperature, then maximum heat transfer would be equal to Q max. Q max is equal to H into area of surface into base temperature minus temperature of the surrounding, and efficiency we know is Q by Q max. So efficiency is given to us, Q is given to us, and we from there we can calculate our Q max, which comes out to be 12 watt. Next is, two infinitely long rod of same diameter, rod 1 and 2, having K conductivity, first rod conductivity is 109 and for second rod conductivity is 400 watt per meter degree Celsius. Having one end inserted in heat furnace, both rod is exposed to same environment and at a distance of 100 mm from the furnace end, temperature of rod 1 is 200 degrees Celsius. So we have to find at what distance from furnace end same temperature will reach rod 2. So this is our furnace end, and rod 1 having K 109 at a distance of 100 mm, sorry, the temperature is 200 degrees Celsius. And for rod 2, and it has K is equal to 400, we have to find at what distance from the furnace at X length temperature would be 200 degrees Celsius. So we know that for infinitely long fin, our theta by theta e is equal to e to the power minus mx, and given is that parameters are same. So m1 x1 for rod 1 would be equal to m2 x2 for rod 2. M we know is h into perimeter upon k1a, and m2 would be h into perimeter upon k2a. From here we can say that our the perimeters are same, so which means heat transfer h would be same, parameters are same, so h would be same, then our perimeter p would be same, and area would also be same because it is said in question that perimeters are same. So this would give us relation that x1 by root k1 would be equal to x2 by root k2. From here we can calculate our x2, which is the length, which would be equal to root of k2 by k1 into x1. k2 is given 400, k1 is given 109, x1 length of the rod 1 from where the temperature is 200 degrees Celsius, it is 100 mm. So from there our x2 comes out to be 191, sorry about that, 191.56 mm.